About 2 years ago now, I designed and built every part of this robot arm right here in my home shop. And I did so without ever having seen a robot arm in person, let alone actually get to use one. So how was I able to figure out what to do and how to make this thing without taking a class and without ever actually using a robot arm? Well, the short answer is I reverse engineered it by studying pictures and video clips I found on the internet. Disassembling machines and figuring out how they work is like one of the most exciting things I do. So I can't wait to take this thing apart. Join me today as we talk about how to reverse engineer just about anything, even if you don't have one. Let's get started. So in the simplest possible terms, you want to reverse engineer because you want to understand how something works and how it was made. And that's not only physical products. You could also reverse engineer code with the intent of understanding the structure of the code and what that code was designed to do. I think for many lay people outside of engineering, you may think of reverse engineering as something like corporate espionage, that you would steal someone's trade secrets or copy their trademarked product. Now, there are definitely rascals out there who would do such a thing, but there are many, many reasons you would do reverse engineering that are both perfectly legal and it's very common. For example, the U.S. military spends millions of dollars a year reverse engineering their own equipment, both military planes, helicopters, and all sorts of other equipment. Of course, they're not stealing secrets from themselves, so why would they do such a thing? Similar to the U.S. military, there are a lot of companies that spend thousands, hundreds of thousands, or even millions of dollars getting equipment manufactured and installed, custom made for them, and then the company who made that equipment goes out of business. So the product's no longer available. But when they need a piece of it repaired or replaced, there's no one to call. So in those cases, you would reverse engineer that product so that you could make your own replacement parts. That's one of the problems the U.S. military is fighting, is when they want to fix one of their planes that was designed and built 30 years ago, they need to make new parts that aren't being manufactured anymore. Well, how do you do it? You have to reverse engineer it. Reverse engineering these old products also gives you an opportunity to reconsider how you might make it faster with modern tools today, and you will need to change the original design to fit the new process. But there are also reasons to reverse engineer other people's products. And as far as I know, no one in the engineering world thinks that there's a problem with that. In fact, we have a name for exactly this called product benchmarking. It's where you tear down either your own products or your competitor's product with the specific purpose of trying to understand how to make it better, how to make it more efficiently, how to improve your product in general. And just in case you aren't entirely convinced that this is an essential skill for all engineers, I was recently asked to contribute some writing as well as review to a college textbook. This is called Product Design Best Practices, the 50 best industry practices regarding product design. And guess what made the top 50 list? Reverse engineering. And this is one of the sections I help write. So most of what I'm going to be sharing with you more casually today is written pretty formally here in this textbook. You can get the book in print, you can get a digital copy of the text, and you can even just purchase one chapter if you like. If you want more information on this and the other 50 best practices, I'll put a link in the description for you. So at this point, you should have a pretty good grip on why you would want to do this. Let's talk about how to do it. This is one of those things that probably goes without saying, but you can certainly learn a lot more when you have access to a machine as opposed to trying to figure it out remotely. But there are a lot of things that you can learn about a machine of any type without being able to touch it. So I thought it would be useful to teach you some of the strategies I use when I don't have access to the machine first, and then we'll work our way into actually disassembling the robot arm. When I first started designing my robot arm, I literally had a blank slate, and there are thousands of variables that go into designing a robot arm. But here's the important thing. Many different companies have already spent thousands of engineering hours thinking about these questions. So it's really helpful to look at a typical robot arm that's already on the market and say, what are the normal proportions of a robot arm? So I decided I should start by just looking at pictures and scaling those pictures. Well, guess what? The internet provides you thousands of pictures of robot arms in all sorts of configurations. There are usually things in the background, and those things in the background can be used as a reference to figure out scale. And that's exactly what I did. Here we're only talking about the mechanical design. We haven't looked at the electrical, we haven't looked at the programming. fabrication techniques. We're just looking at the general shape and dimensions. And of course, your final design will be different and it'll be highly specific to your design goals. But you don't have to repeat all the troubleshooting and mistakes that others have made for you in advance trying to do something similar. So images would be number one. Those are abundant on the internet and readily available. The second thing would be user manuals. Every product has some kind of user manual. Even if you buy Bluetooth headphones, there's going to be some sort of basic manual. And one of the most important things you can get out of the manual is troubleshooting. One of the reasons I like to go to the troubleshooting section first is because it teaches you about common problems with this product. All of the replacement parts for this thing have been pointed out. They've been labeled. And this is a good place to start if you want to reverse engineer this product. Well, many of the parts have already been labeled by a manufacturer, giving you a name and so on. And that's going to become important a little bit later when I teach you about disassembling the physical product. If this is a very heavy product, there's often going to be a diagram showing you where to put slings for lifting this device properly. It'll tell you where the center of gravity is. It'll tell you how much the product weighs. If you're looking at the product manual for a robot arm, there are usually multiple product manuals because there will be one for the electrical cabinet. There'll be one for maintenance that shows you how to repair and replace parts, how to lift the machine. So it really depends on the product. There are a bunch of other resources online. For example, looking for YouTube videos. Someone may have already torn down this product for you. Product reviews can reveal a lot of information similar to the troubleshooting guide. Customer reviews right on the page where you might purchase the product can tell you a lot about what customers like and don't like about the product, its usability, and so on. Websites will often have a frequently asked questions section. Again, another place to look for information that may be helpful in you understanding this product a little bit better. Also, the manufacturer of the product will often have tutorials on how to use the product properly, the user interface. Another thing you should search for is research papers. You can see if they've published anything about their innovative design. They've invested all this time in the lab figuring out how to make it work. And then they publish a paper telling you exactly what happened. And this is true for software and hardware. Google has a whole research section on their website called Google Research, where they publish stuff about YouTube, about the algorithm, about the various statistics and things that they figured out. If you're interested in learning from their software design experience, you may find that information in Google Research. As we saw in the first part of this series, link in the description, large products with electrical usually have a schematic, but you can also download those schematics online. And even if the product is pretty small, you may be able to find a schematic online. So this is something you should look for. And finally, I want to mention 3D models. Very often, especially for industrial products, there will be 3D models available online from the manufacturer. It will be a dumbed down model. It won't have all the interior structures so that you can see if this thing will fit in your factory, so on and so on. And less reliable, but still available, you may find models on these aggregate websites like GrabCAD where people are uploading models that they've created themselves. And so you just have to trust that they've taken good measurements and that it's actually a representative model and not something that just looks like it. So at this point, you've got a sample of the kind of things that you can learn about a product without having access to one. But of course, in this case, we actually have one. So what do you do when you have a product in front of you? If you have more than one of them, which would be the ideal circumstance, you can start tearing it down right away. Take lots of pictures and document the whole process. I'm going to explain that in more detail in just a minute. If you don't have more than one, you got to be really careful because there are plenty of machines where parts are glued together permanently or welded together permanently, and you may have to take a grinder or something to open those parts up to see what's inside. Once you've done that, it's somewhat irreversible. You can also save yourself a lot of trouble by not having to reassemble the whole thing, whatever it is, in order to test some feature that you forgot to test in advance. Once you've completed all of your physical testing, everything that you need to do when it's fully functional and fully assembled, then you can start moving into your decomposition. Now that we're finally ready for decomposition, we can remove one piece at a time. As each piece is removed, you will take photos of it, give that piece a name, describe its functionality, and also document how you removed it so that you've got a written record of how to put this thing back together if you want to use it again. And especially if you're working with a team of engineers, this is extremely important because 2 years later, you're not going to remember any of this if you didn't document it well. So writing it down, makes all of this simple. Now, we actually have a template for you that will make this really simple. It gives you a place to put the name, its function, etc. Now, you can print these templates out and write on them, but ideally you would use the spreadsheet because there's a place for you to insert pictures, the pictures that you take while you're breaking things down. And the digital format not only allows you to resize these pictures later, but obviously make updates to the text without having to print out new paper. These templates are completely free. You don't have to order the book to get access to one. You just need to go to the website and download it. Well, hopefully this seems obvious, but we're going to go ahead and disconnect all of our power and control cables before we start removing anything. Okay. Before we start to tear down, I want to talk about a really essential piece of hardware, which is fasteners. We're going to be removing a lot of fasteners today, different thread pitches, different lengths. And so it's important that you keep track of these fasteners. And I'm going to show you how I keep track of them in just a minute. But occasionally you lose or break some anyway, which is why I have this area over here. So here I have all of the standard size fasteners that I find myself using over and over in every project. In fact, I don't think I have a project that doesn't use fasteners. I've got both metric as well as US customary units here. And I've got a few smaller ones that I buy in these little bins like this. But even with this, I still run into situations where I don't have the fastener I need. And that brings me to my sponsor, Accu. Accu is both here in the US as well as in the UK. And they have every kind of fastener you can imagine readily available on their website. The part that was most astonishing to me about using their website is you can order literally one fastener. How many times have I needed just one or two pieces of something and you have to order a box of 25 or 50? It's ridiculous. So I was shocked to see that you could literally order like one M8 thread and they will ship you just that one if that's all you want. So anyway, the prices are good. They're 3D models on the page for every kind of fastener and pretty much all of the products that they sell. I'm really glad to have them as a sponsor because they really offer a fantastic service. Shipping times are really quick here in the US. I'll put the link here on the screen, but I'll also put it down in the description so that you can just click on it and go straight to the website and look for whatever you want. I also want to mention that they make custom fasteners, which is a whole nother level of engineering that's available to you. But I want to caution you, if you can use a standard fastener, I definitely recommend you do that before you order a custom fastener. But sometimes you really need a custom fastener. And if that's the case, you can design it right on their website. And you can also reach out to their engineering staff and they'll help walk you through it to make sure you're getting exactly what you need for your project. So anyway, check out that link in the description. And thank you again to Accu for sponsoring this video. All right, let's get to that teardown. So there's no hard and fast rule about what to remove first, but I generally like to start with what looks like the simplest component on one side, and I will work my way until I've gotten everything removed. I told you earlier that you should carefully document this process, but watching someone fill out paperwork is ridiculously boring. So for video purposes, I'm simply going to remove the pieces and just talk to you about what I learned along the way. All right, that's stuck on there pretty good, but it looks like I've removed all of the fasteners. Okay, actually, this is kind of interesting. So the whole reason we're doing this is to discover the engineering tips and tricks that we can get from the people who designed this machine. Now look, this piece is painted after it's been assembled, right? And if you look, there's a little divot there where I can stick a screwdriver. I was literally just thinking I may have to pry this off. And what do you know? There's a convenient place to pry this off. I think that's intentional. Maybe that's there for something else, but it sure looks like it's there for what I might want it for. So let's give it a try. And there's one on the bottom. Look at that. I love it. Ooh. We've already got something pretty interesting here. Look at that. This part's been machined. Why did they machine that? I would expect them to machine this face, but not to also go in here and make this thinner here and here. Now I could go to speculate to why they would do that and maybe why they couldn't change the casting to eliminate that step, but that's something we can figure out later. For now, I just want to take pictures of it and pay attention to the fact that they spent money on this feature, and that's interesting. So right away, we can see that this pulley is driving this larger pulley. We've got an electric motor here, looks like a servo motor with an encoder on the back. What's interesting is the position of the motor relative to this pulley. Unless this motor is connected to the other side of this, I I don't know why it's oriented in this position, but we'll find out in a minute when we take the other side off. We can see there are actually two servo motors here. One driving the gear mechanism on this side, and that looks like 1-to-1. And then over here, we can see this is closer to 2-to-1 maybe. I haven't measured that precisely, obviously. I'm also surprised at the size of these motors. I expected them to be slightly larger, but apparently you don't need as much power here as I initially thought to get the kind of performance that this machine can put out. Okay, here we have a harmonic drive. You can see that the cup is flexible there. Little ring to seal everything in, a gasket. I think it's worth reiterating here that I have never done this before with an industrial robot. So for those of you who do maintenance on these kinds of machines, I am entirely certain that I'm doing something in an order that you would not prefer. But that's okay. This is how we learn. We're figuring it out. Be sure to leave me a comment and let me know what I should do next time. Okay, I need 3 cameras to show you how this works. So basically on this side, you can see there's pretty significant reduction between this pulley and this faceplate. So hopefully we'll get a look inside of there in just a moment. But there's a gear reduction there to rotate axis number 5 up and down. This motor right here is driving axis number 5. So the one on top is driving axis number 6. And as you can see, if I tilt that down a little bit, you can see that faceplate moving. But there's an interesting side effect. Let me hold it still. When you move number 5, you can see the faceplate also wants to move. So what they have to do is within the program, they compensate for that by moving axis number 6 in the opposite direction. So if the faceplate would tend to rotate to the right whenever you're moving up, I'm making that up, then the motor needs to move the faceplate to the left or in the opposite direction by the right amount to compensate for that movement. So at this point, I've removed all the fasteners and I'm ready to take out axis number 6 and keep working my way forward. But there's no obvious way to get this piece out, but there is a clue. If you look really closely, you'll see, let me just zoom in here. Here you can see that all of these holes are through holes except these two, which are equally spaced apart and they're a different size thread. And the same on this outer ring, all of these holes are through holes except these two. Equally spaced apart, different size thread, and they don't seem to have any purpose. There was no fastener in those holes when I started this. So that's a good indicator that these holes have a different purpose, and I believe these are put there for jack screws. So a jack screw is just a fastener that you use to literally push out the piece that has been wedged into place. So this is a press fit. It's really tough to pull this out, but a jack screw gives you the leverage to push out press fit pieces. I've seen this with all sorts of pulleys that clamp onto shafts and different types of collars. So I'm pretty confident that that's what they intended here, and that's what I'll do. Yeah. All right, as you can see, there's another harmonic drive here. This is the flexible cut part. And harmonic drives are really fascinating, actually. I made a whole video about this, so I won't talk about it much here, except to say that there's this egg-shaped bearing that's in here that causes this cup to wobble around, and that makes for a huge gear reduction in a very small space. They're super fascinating, so I have a whole video about that. I'll put a link for you in the description. You should check that out. Now we should be ready to remove this piece on the other side, and then I can slip this guy out. Woo. There it is. Look at that. We got it out. There's a pretty thick wad of grease in there, making it difficult to see the bevel gear down in there. Maybe we'll clean that out in just a minute. But you can see the bevel gear on this guy. Look at this. That is a beauty, my friend. Oh, I love engineering. Somebody designed that bevel gear. Okay, let's keep going. I think I'm ready to take the motors out, but before I move to that step, I want to point out something interesting here, and that is there's some features I'm not sure what they do. Like there's this port that has a fastener inside of it. I don't know if that's there for some sort of machining step that's not needed later, but it gives you an access hole to the inside. There's nothing on this piece that is immediately obvious what it lines up with. Oh, well, there's a divot there. Okay, wait, never mind. I might have spoke too soon. So this is speculation. I don't know, and I would love for you to tell me if you do know in the comment section if that's for alignment of some sort. It might be a pointed fastener that goes into here. You put it into place, tighten down that fastener. As best I can tell, that's the only thing that lines up with it. I may have just answered my own question, but obviously I don't know for sure, so don't quote me on that. In fact, tell me if you know. You should definitely take note of any features that you don't know what they're there for, because they may have been put there for some sort of machining step during fabrication. They may be there for maintenance steps that aren't used regularly. For example, the 2 tapped holes that I just showed you to jack those pieces out. Anything that looks like it was put there on purpose is worth writing down and paying attention to. Of course, when you have a belt drive like this, you need to be able to tension the belt. And if you zoom in, there are slots for tensioning the belt. So that's nice for maintenance. If you have problems with the motor, you can easily remove it. These AC servo motors have a corresponding controller in the electrical cabinet. So if I wanted to reuse these in another project, you know where this is going, huh? Perfect. If I do this carefully enough, I should be able to reconnect all of these motors outside of this assembly and power everything from the control cabinet. And then we should be able to see how the individual motors move when we input certain types of controls. That actually sounds pretty interesting. Now, I've said this a couple of times, but it's worth pointing out again that everything that required additional work is worth paying attention to. So somebody was paid to take the time to cover up these wire connections with this waterproof cover and then zip tied it shut. Presumably this is to keep any grease or oil or whatever from potentially contaminating these circuits. And this is done everywhere that there's a break in the wire. And you should note that it was put there, how you might be able to do it better if you're improving your own product, and if you even need it at all. Because just because someone in the past thought it was a good idea doesn't mean it really is. Okay, I say that, but actually you should never be so conceited to think that you're smarter than the guy who came before you, especially if you're looking at a pre-existing piece of equipment, because they may have been like you. They may have designed it without it and then added it later, again, for good reason. Maybe a good rule of thumb is to say to yourself, if you look at a piece and you instantly think, why did they do it that way? There's a good chance you just haven't thought about it long enough to realize why they did what they did. Don't assume you're just smarter, even though you have no experience. I think it's much safer to assume that they're average and you're average, and you should pay attention to their experience. I decided this is a good time to go ahead and put some of the fasteners back in. This just makes it easier for me to keep track of where the fasteners came from, and I don't have to worry about sorting or labeling them. They are where they belong. Okay, next we need to get those fasteners out. I want to point out that there are also threaded holes, again, presumably for jack screws. To access these fasteners, you would want to use something like this that will give you that 90-degree offset so that you can get the tool inside of there. All right, here we go again. We've got a faceplate that's painted on, and down here, there's a little place to insert your screwdriver. I love the fact that this just makes sense, and I've never done this before. There we go. Oh, God. Looking closer, we can see the faces aren't just painted on. There's like a liquid gasket or some kind of sealant in there as well, making the face stick. Now I find myself looking for the place where the screwdriver is supposed to go. Oh, here it is. Nice. Oh, wow. Again, this motor is smaller than I expected. Oh, but look at that harness. That's beautiful. Nice and neat, organized. I like it. I can't help but stop at each stage of this and just admire all the things that I didn't know about designing robots as I look at this professional one and compare it mentally to the one that I made. For example, there's some problems I did anticipate, like I made quick disconnects so that I could disconnect the servo motors at each stage. I have that. But then there are things that I didn't really know was an option. For example, this metal wound tube, if you will, that is protecting the cable. It's flexible, but it's also very small and it fits inside the robot. And then they've got this pass-through joint here, which I'll show you more of in just a minute. It's really neat. Now all the cables are inside the robot instead of outside the robot, and I have to manage wherever they go and risk them getting tangled or caught on something when the robot is working. You eliminate that problem by making the cable on the inside. So these are all lessons learned. I would know to look for something like this now to be able to connect, run cables on the inside. I can tell a lot of thought went into making this work the way it does. And this robot is 20 years old. This is 2007, so almost 20 years old. Surely they've made additional improvements since then. So here we have the harmonic drive cup directly coupled to this piece here. And as you see, when the motor drives that harmonic drive, this is the output on the front. And you can see there's a bearing there and a bearing here to support that spinning. But even more interesting is this offset shaft. Now you might be thinking, well, if this thing keeps spinning, it's going to tangle up the cable, right? But actually, through programming, you don't tangle it up because there's no need for this end to go all the way around. It'll go so many degrees this way and then so many degrees that way. I'm just roughly approximating. I don't know what the actual limits are. But if it's here and here, you would see the cable would never get tangled up. So here's another thing that I spend a lot of time thinking about whenever I'm tearing down a machine, and that is, how did they make it? For example, this part is definitely cast, right? And then there's some post machining. But what's interesting is, the center of this hole where the motor is driving definitely needs to be concentric with the bearing here. How tight does that fit? I'm not entirely sure, but I do know that there's some kind of decent tolerance on it. And that leads me to the question of, well, how do you hold this? Maybe they machine this face first, bore all the way through, and come out the back would be my educated guess. I'm not a professional machinist. I'm just thinking about how I might approach this for the first time. And then you've got a hole here in the center, and now you can line up on that hole and machine all these faces. And then you know that you've got pretty good concentricity. But in order to machine it like that, you're gonna have to take it out of the vise at least once, and thus set it all back up again, make sure it's flat, on and on. And so that increases the chance that you may not hit your concentricity. But then again, maybe the tolerance is such that even if you take it out of the vise and you're really careful with it, you can still get it lined up. Although I am just thinking about a standard 3-axis machine. If you put this on a 5-axis machine, you wouldn't have to take it out of the vise. And then it would just be the tolerance of the machine itself that could roll the part all the way over, and then you continue machining from the other side. So actually there are a couple of options, but operating a 5-axis machine costs more money and takes longer to program. But really the reason I'm bringing this up is because it's helpful to start thinking about how they approach this problem, because if you want to make something similar, or if this is your part and you want to improve upon it, this is your opportunity to think about how you can do it better. Here's a good opportunity to talk about the difference between casting and machining. Here you can see there's a really intricate shape here that will be extremely difficult to machine. It's not impossible, but casting is a much better application of this kind of shape, and something to consider when you're deciding what method you want to use. If you're not mass producing these, casting feels like the expensive option, right? So you'd want to think about ways to do this with machining if you aren't going to make very many of them. But here, they're making thousands of robots, so casting is the obvious choice for multiple reasons. You can get these unique shapes, but it definitely decreases the cost with volume. So there's that too. And here we can see there's yet another harmonic drive for axis number 1, and that rotates the base around this axis. Well, I hate to interrupt this teardown, but I've had a rather traumatic mechanical failure. I've had surgery on my leg, which has put me in a cast and made this extremely difficult to continue tearing this thing apart. If you want to know more about what happened, I will put a link right here that you can click on and watch that video. As you can see on the table behind me, we did make quite a bit of progress. I really hate to stop when I'm so close to being finished, but trying to do this while maneuvering on crutches is not only a little bit dangerous, but also extremely tiresome and time consuming. So I'm gonna rest this leg like I'm supposed to and call this video done where I am. So even though I didn't get to finish the teardown, I did finish what I set out to accomplish, which was to show you the process of tearing down this machine. And we got to see all of the vital parts going down to the very last 2 stages here of the robot. In the future, I may post some YouTube shorts that will show you the last little bits if people show a lot of interest in that. And I would love to answer any questions you have about this whole project. Leave those things down in the comments and I would love to talk to you about it. Anyway, I hope you've enjoyed this video, and as soon as this leg is good enough for me to get back in the shop, we'll start working on the next project. Thanks for watching.